Yes, I want to talk to you about closures and Rust verification specification. This was a joint work with Christoph, Alex, and Peter, and based on a master's thesis by Fabian Wolf. So my first claim is that reasoning about closures can be difficult. And to convince you, let me show you an example in everybody's favorite language, JavaScript. So here we have some function foo. It takes an object O, we assign 1 to this field X, and then we create this closure counter. So this is a function which it's a closure because it captures the environment from the outer function. Notice that O is not a formal argument here. And what it does, it increases the value of this field and returns the new value. And so in this case, it should be pretty obvious that this call counter here will return 2 because it incremented 1 and then returned it. But as soon as we add this quite innocent looking bar function, things already start to break down. Because I could have implemented this bar function this way, where I set the X field of this object to 42, and there's basically nothing protecting us from this O passed to foo being the same as the same O. And so in this case, the function would actually return 43. And so the point of this talk is, of course, that JavaScript sucks. No, you can do the same thing in Scala. You can do the same thing in C++. In Python, you can pick, any language which supports this kind of closures. And so Rust helps us a little bit here. If I want to do the same thing here in Rust, if you are not familiar with the syntax, believe me that it does the same thing. This bar call here cannot actually modify the object O. And I can inline this call this way. So if I try to directly say O.x is assigned to 42, well, I get a very verbose error, but basically the compiler is complaining to me that this O.x is borrowed by the counter and therefore cannot be modified by other things. And so the type system in Rust helps us because when a closure captures its environment, it actually captures it, which entails ownership. And so this helps us, but of course we actually want to talk about specification and verification of closures. So we got this memory safety, but we want to reason about individual executions of closures, of unbounded sequences of calls, and of higher order functions such as map and filter. So before we get to that, let me just very briefly introduce Prusti, the Rust verifier that we developed at the program methodology group at ETH. So here we have a very simple shift function which takes a two-dimensional point and shifts its x-coordinate by the argument. In Prusti, we write annotations and specifications using the Rust annotation syntax, so I can add a precondition saying that I can shift by more than 2 only. And I can add post conditions such as this, where I'm saying that the object is indeed shifted on the x-coordinate and the y-coordinate remains the same. Crucially, in Prusti, we do modular verification, so the contract of the method is all that should matter for verifying other methods. So let's move back to closures. So let's explore one particular class of problems. So here we have the same kind of counter as before, but now I call it once and then a second time to obtain 2 values. And to make this more interesting, in between these 2 calls, I have a loop calling this counter some number of times. And here I know nothing about n statically, so basically this can execute any number of times, including 0. And the property that I would like to show at the end is that the value that I obtain from the second call is not smaller than the value I obtained first. So some kind of monotonicity. And so what are the problems? Well, we know the state very easily at the beginning. We can easily infer the state after the first call. But because of this problem with not knowing n statically, we actually lose information here. And so how do we actually get to this assertion? So if we represent the state of O of x, then it's roughly like this. And of course, as soon as we enter this loop, we lose the information. But what we can say about the state evolution is, well, at every point, I am definitely going to get a larger or equal value than the previous one. And we can express this as an invariant, or what we call a history invariant for closures, which is actually a two-state property relating any current state to any previous state. And notice also that we use greater or equal because this should also hold across zero calls. And with the post condition of also saying what the result of this closure is, we can actually statically verify this assertion. And notice that if I make another small change to this function where I pass the counter closure to an unrelated function, no matter what this other function does, I know that the invariant of counter will be preserved. So I can still prove this monotonicity after all. So our solution to this particular problem was history invariance, and we noted that the Rust type system helped us here because we know what can modify the captured state of the closure, specifically just the closure. Okay, now let's talk a bit about higher order functions. So again, syntax notwithstanding, this is basically just a function which takes a closure from an integer to an integer, and it tries to call this closure with the argument 5 and show that it's not a negative number. But of course, I could be evil and pass to this higher function a closure which always returns -1, making this assertion fail. So how do we actually specify the requirements for the caller of this higher function? And so for this, we use a specification entailment, which essentially says what is the apparent contract of the closure as you can see it within this higher function. Something that should hold for all the future calls of the closure within the higher function. And so basically we say, well, okay, this will be a closure that expects a positive argument and ensures that its result will also be positive. And so if we have such a contract, if we know that f satisfies this contract, then of course this assertion also holds. And so now let's consider a concrete client code and a concrete closure that we would like to pass to this higher function. So here we have some closure which basically it just multiplies its argument by 2, and this is its result. But additionally, it performs this unrelated operation, which would be undefined if I was -5. So we add this precondition that I cannot be -5. So now, can I pass this closure to the higher function? How can we check this? And so the way we solve this particular kind of check is we expect the specification in CL to be at least as strong, or stronger, of course, as the contract that HOF expects. And so more concretely, this means that the precondition as expected by HOF implies the precondition of the concrete closure, right? So that when I call it here, I know that this contract will definitely be satisfied. And likewise, if I did call this function with this precondition, then the postcondition of the concrete closure should definitely entail this postcondition that the higher the function expects. And well, these two implication checks might be familiar to you. This is, of course, a behavioral subtyping relation. So basically, we notice that it makes sense for specifying higher functions to let's say, limit the closures not by just the signature, but also by the contract that we expect. And of course, then this call is in fact valid. So these were our solutions to this problem. Once again, we thank the type system because without knowing that other parts of the code cannot modify the state captured by the closure, we wouldn't know that its contract cannot be violated by external changes. Okay, let's go back to the same example. The precondition remains the same, but I make a small change here where instead of this assertion, I make the higher the function just return the value of the closure call. Now it's just passing it to the client side. And of course, this property here holds because I am passing this closure, which multiplies the argument by 2. The higher the function calls it with 5, so the result will be 10. How do I say anything about the result of this higher function? So I cannot say result equals f of 5 because this is a closure. This is not a pure function. It might have side effects when I invoke it. So what we have as a solution is a call description. So this is you can think of it as an effect, or you can think of it as a record of the closure having been called with certain arguments and with certain facts holding in the pre-state and the post-state. So more concretely here, this higher function says that the function f will be called with 5 being the argument and with the result of the closure being the same as the result of the higher function. So here we, in the post state, we can access the result returned by the closure, and we use outer to disambiguate between the result of the higher function and f. And with that, we can actually prove this assertion statically again. Note that this contract by itself isn't enough. It's at this client side that we know the concrete contract of this closure that we can compose it with the call description to actually get this property. So yeah, the problem was that we wanted to specify higher functions without relying on any particular specification of the closure and trying to be parametric in the actual kind of closure that you can pass. And so for this, we used call descriptions. And once again, the Rust type system helps us here because in the call description, we talk about pre-state and post-state of the call, and it only makes sense to talk about things that the closure can actually modify. We know that the call will not modify random other parts of the state. And so we have evaluated this as part of the Prusti verifier. There's some artifact if you want to go there. This is based on top of the Viper verifier, which ultimately encodes things into assembly queries for Z3, which means that our methodology cannot be a higher order logic. We needed to actually find a first order logic encoding of this. So our basic evaluation at the time was a couple of examples from the literature of particular problems with closures. For example, this blame assign was to make it clear which part, whether it's the call side or the higher function, carries the blame for an assertion failure. We also evaluated various cases from the Rust standard library, such as mapping a function over a vector. We used history invariance in some cases, specification entailments always, and sometimes call descriptions with relatively okay verification times. Okay, so to summarize the contributions, we have developed a new specification methodology for closures, including these history invariance, specification entailments, call descriptions, and also some parts which were not shown here, such as these ghost predicates, pure closures that you can pass to all further parameterize the specifications of things like fold. We encoded this methodology in first order logic such that it's actually automatable. We implemented it as part of Prusti. We had some analysis of how closures are actually used in practice based on large-scale evaluation of crates in the Rust ecosystem. And yeah, and so this is the state as of last year. There are some changes, I guess, since then. In particular, this methodology that I presented here is not hard-coded into the verifier. It's something that you can actually write using traits and certain features that we added to Prusti, so that you can basically develop a closure methodology in user-facing syntax. And we noticed, so we further worked on iterators in Rust, which carry some very similar problems to this. In particular, things like map and filter here are functions which are somehow parameterized by a closure, and you need to describe in specifications how they actually interact, how the final collection will look like, and so on. Yeah, thank you.
Two questions nearby.
Do you have any idea how to handle interior mutability in Rust?
I would say that's not related to this talk, but yes, we are working on it as part of the Prusti group. But it's not my line of work, so I cannot tell you very much about it.
But I think that some of those assumptions you make about the state not changing when you call a closure might not actually be true.
True. Things where interior mutability actually matter can be marked in my colleague's work with basically annotations saying, well, these parts are not as stable as they would be if you just had shared references, for example. So then it becomes, so when you have a shared reference, then it's not just the shared reference, but you need, for example, also a heap version to deal with successive changes of interior mutability data.
Thank you.
Your question is answered.
That was my question. Already.
Any other questions? I have one question. You mentioned about these specifications for calls. You call them
Call descriptions.
Yeah, call descriptions. So, is there a support already for specifying calls that, or specifying the order among calls, apart from just having a single call?
Yeah, so this was a limitation in when we wrote this. We noticed that a call description is kind of a relation between not just the state of the arguments, but also of the closure itself. And so now, and also in the iterators work, what we can write as a call description is a certain method was called, which in the case of closures is a fn mute call mute, representing the call operator of a closure. And in the pre-state and post-state, you can say, well, the receiver of this call was a particular state, and the receiver in the post-state was a different state. So you can store intermediate versions of the closure, for example, in a ghost sequence to basically establish a sequence of calls. And this is something that you can use to handle things like a map iterator.
Okay, so that's already work in progress.
Yes.
Yes, we have one more
Thanks
question.
for the talk. I just have, maybe I missed out some of the information, just that how do you encode the specification for fold left or fold right, either of it? But you also like to use the chain of some these functions, or do you have a solution for that?
Yeah, so this was one of the parts not presented with ghost predicates. Essentially, it's like a higher order function, but we noticed that basically you can rewrite something like a fold to a loop, and so it's quite natural that you would need something like a loop invariant to verify this. And so the call to a fold needs to be parameterized by something like a loop invariant. And so in our work, this is a ghost predicate, or basically a pure closure, which says, okay, this summarizes the progress of the loop thus far. And yeah, this then leads you to a specification of fold where you can sort of plug in the ghost predicate that was passed in at the call site, and you get a full proof of the fold.
I see, thanks.
All right, so thanks, Aurel, again for the talk.
Thank you.